The general section formula. Welcome, everyone. Before we dive into today's new material, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored the fundamental concept of internal division, where we actually looked at the geometric proof of the section formula by using similar triangles to see how the ratios relate to the sides. Now, we are going to shift our focus toward the practical application of the general section formula. While drawing triangles is great for understanding the why behind the math, it isn't very efficient for solving complex problems. Today, I will show you how to use this formula as a powerful tool. This will allow you to calculate the exact coordinates of a point that divides a line segment into a specific ratio directly and efficiently, without the need to draw triangles every single time. Let's get started. Understanding the concept. Now that we've introduced our topic, let's take a closer look at what we actually mean when we talk about internal division. Imagine we have a line segment, let's call it OB. When we say a point, let's call it P with coordinates x and y, divides this line segment OB internally in the ratio m1 to m2, there are two very important things to keep in mind. First, the point P must lie directly on the line segment OB itself. It's sitting right between the two endpoints. Second, the ratio tells us how the segment is split. It means that the distance from point A to point P, compared to the distance from point P to point B, follows that specific ratio of m1 to m2. To put this into a mathematical expression that you can use for our calculations, we write it as the fraction AP over PB equals the fraction m1 over m2. This simple equation is the foundation for the formula we are about to see in the next slide, as it represents the relationship between the segments and the ratio. The general section formula. Suppose we have any 2 points, point A with coordinates x sub 1, y sub 1, and point B with coordinates x sub 2, y sub 2. If we want to find the coordinates of a point P, which we'll call x sub P and y sub P, that divides the line segment OB internally in the ratio m sub 1 to m sub 2, we can use this formula. The coordinates of point P, x sub P, y sub P are equal to the following. For the x-coordinate, we take m sub 1 times x sub 2 plus m sub 2 times x sub 1, all over the sum of m sub 1 and m sub 2. For the y-coordinate, we follow the same pattern. M sub 1 times y sub 2 plus m sub 2 times y sub 1, all divided by the sum of m sub 1 and m sub 2. What is great about this formula is that it provides us with a direct algebraic method. Instead of having to draw similar triangles and solve for unknown lengths every single time, as we did in our previous lessons, we can jump straight to the answer. As long as we know the coordinates of our two endpoints and the specific ratio we are working with, we can calculate the exact position of point P immediately. In the next few slides, I will show you exactly how to apply this step by step. Now that we understand the concept of a point dividing a line segment into a specific ratio, let's look at the actual tool we will be using, the general section formula. Step-by-step guide to applying the formula. Now that we have seen the formula itself on the previous slide, you might be wondering how to actually use it without getting overwhelmed. To make things easier, I've broken the process down into 5 manageable steps. First, you need to identify the coordinates. Before you do any math, clearly list the coordinates of your two endpoints. We will call the first point A with x1 and y1, and the second point B with x2 and y2. Writing these down clearly prevents confusion later on. First, you need to identify the coordinates. Before you do any math, clearly list the coordinates of your two endpoints. We will call the first point A with x1 and y1, and the second point B with x2 and y2. Writing these down clearly prevents confusion later on. Second, identify the ratio. Look at the problem and determine what your m1 and m2 are. This is the ratio that tells us how the line is being divided. Third, we move to the calculation phase. You will substitute these values into the x-coordinate formula. You'll take your m1, m2, x1, and x2 and plug them into the expression m1 times x2 plus m2 times x1 all over m1 plus m2. Fourth, you do the exact same thing for the vertical component. Substitute your values into the y-coordinate formula. This means plugging m1, m2, y1, and y2 into the expression, m1 times y2 plus m2 times y1 all over m1 plus m2. Finally, the fifth step is to simplify. This is where you perform the arithmetic, the multiplication, the addition, and the division to find your final, clean values for x and y. If you follow these steps systematically, as we are about to see in our real-world example on the next slide, you'll find that even complex problems become quite straightforward. Real-world application example. Now that we have mastered the theory and the formula, let's put it into practice with a real-world application. Imagine you are a network engineer working on a city map. We have two cellular towers located at specific coordinates. Point A is at 2, 3, and point B is at 8, 11. These units are measured in kilometers. The goal is to place a signal booster at a new point, which we will call point P to ensure maximum coverage. This booster needs to be placed so that it divides the distance between the two towers in a ratio of 2 to 1. To solve this, we are going to follow the step-by-step guide we just discussed. First, let's complete step 1, identify the coordinates. From our scenario, we can clearly see that the x-coordinate of our first point, x1, is 2, and the y-coordinate, y1, is 3. For our second point, the x-coordinate, x2, is 8, and the y-coordinate, y2, is 11. Next, we move to step 2, identify the ratio. Based on our requirement for the signal booster, our ratio, m1 to m2, is 2 to 1. Now that we have all our values organized, in the next slide, we will plug these numbers directly into our general section formula to find the exact location for our booster. Real-world application example, continued. Step 3 is where we find the x-coordinate of our point P. We'll start by writing down our formula. X equals m1 times x2 plus m2 times x1 all over m1 plus m2. Now let's plug in our specific values from our cellular tower example. That gives us x equals the quantity 2 times 8 plus 1 times 2, all divided by 2 plus 1. If we perform the multiplication in the numerator, we get 16 plus 2, which gives us 18. Finally, dividing 18 by 3, we find that x equals 6. Next, we move to step 4 to calculate the y-coordinate of point P. We use the same structure for the formula. Y equals m1 times y2 plus m2 times y1 all over m1 plus m2. Substituting our values, we get y equals the quantity 2 times 11 plus 1 times 3, all divided by 2 plus 1. Multiplying these out, we have 22 plus 3, which results in 25 divided by 3. When we calculate that division, we get approximately 8.33. So, to wrap up this example, our final result shows that the signal booster should be placed at the coordinate 6, 8.33. This gives our engineers the exact location needed to divide the distance between the two towers in that 2 to 1 ratio. Now that we have identified our coordinates and our ratio from the previous slide, let's move on to the actual calculations. Common mistakes to avoid. First, let's talk about swapping coordinates. This is perhaps the most frequent error students make. It happens when you accidentally multiply the first part of the ratio, m1, by the first x-coordinate, x1, and m2 by x2. To avoid this, I want you to remember the cross-multiplication logic. Think of it this way. The ratio part that is near point A, which is m1, must be multiplied by the coordinates of the opposite point, which is point B, containing x2 and y2. Conversely, the ratio part near point B, which is m2, must be multiplied by the coordinates of point A, which are x1 and y1. Always pair the ratio from one side with the coordinates from the other. Next, be very careful with the ratio order. You must ensure that m1 corresponds specifically to the distance starting from your first point, A, and m2 corresponds to the distance leading to your second point, B. If you flip the ratio, your point P will end up in the wrong location on the line segment. Finally, watch out for simple arithmetic errors in the denominator. When you are calculating the bottom part of the fraction, always remember that the denominator is the sum of the ratios, m1 plus m2. A common mistake is to accidentally subtract them instead of adding them. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small mistakes that lead to the wrong answer. Keep these 3 points in mind, and you will find that applying the formula becomes much more reliable. Now, let's move to our final slide to review the key takeaways from today's lesson. Key takeaways. First, remember the primary purpose of the section formula. We use it specifically to find the coordinates of a point. Let's call it point P. That divides a line segment connecting points A and B into a specific, given ratio, which we denote as m1 to m2. Now let's look at the formula itself one last time. The coordinates of point P, which are x and y, are calculated as x equals m1 times x2 plus m2 times x1, all divided by the quantity m1 plus m2. And for the y coordinate, it is m1 times y2 plus m2 times y1, all divided by m1 plus m2. As we saw in our cellular tower example earlier, this is a powerful tool for direct calculation. A great way to think about this mathematically is that the coordinates of point P are actually a weighted average of the coordinates of our endpoints. A and B, the ratios m1 and m2, act as the weights. Finally, a very important reminder. The formula we have practiced today is applicable only for internal division. This means the point P must lie strictly on the line segment between point A and point B. All right, we have reached the end of our lesson, so let's wrap everything up with our key takeaways to ensure you have a solid grasp of the material. I hope this summary helps reinforce what we've learned today. Keep practicing those substitutions and watch out for that common mistake of swapping your coordinates. Great job today.